Coming to this workshop and hopefully making it a great success to start off our 4-month programme. I'm Kevin Horsburgh from the National Oceanography Centre, and along with John T. Rouget and Peter Cox, I helped organise this first workshop. We will be chairing the sessions very lightly, only to take questions in a particular order and to truncate the discussion at the coffee break time, at which point people are very welcome to carry on any discussions out in the area where coffee is served, which is just around the corner there. So apart from that, and without further ado, I'd like to hand over to Tim, who's going to give us our very first and most appropriate talk to get the workshop going. Yeah.
Well, thank you, Kevin. It's a very great honour, I think, to give this first lecture in, I think, what will be a very exciting week, and in fact exciting. How many months is it? 4 months, yes, of programme. Kevin asked me to give a talk about some grand challenges in climate prediction, climate science, and initially I thought I would indeed give a fairly sort of broad-ranging talk covering lots of different challenges that we face. But the more I focused on this talk, the more the number of challenges that I thought I would address actually shrank to a smaller and smaller number. But nevertheless, keeping invariant the product of the number of challenges multiplied by the grandness of the challenges. And I've actually ended up in a rather limiting situation of actually now only going to talk about one challenge, but it's extremely grand. So in that sort of multiplicative sense, I think I've kept to the the sense in which I was asked to talk about. Now, I'm going to kind of leave it as a bit of let's say cliffhanger as to what exactly this grand challenge is, although it'll become, I guess, more and more apparent as the talk goes on, hopefully. But I'll leave the precise formulation of it to the very end, to sort of keep you on tenterhooks. We're talking about mathematical models of climate, and in some sort of very broad brush sense, I want to start by classifying all models into one of two types. Now, I realise this is a bit of a sweeping statement, and I know there are many arguments about hierarchical structures. But in the following sense, I want to just think about two types of models. The first type are idealized and mainly, let's say, mathematically tractable models of climate. So here is a classic case of an energy balance model. If you think you know what the albedo A of the Earth is, and you know the amount of energy that the sun emits, then you can and assuming the Earth is some sort of black body radiator, you can calculate, roughly speaking, some temperature for the Earth. And you can generalize this in certain ways, and indeed this type of model could be used well to demonstrate the greenhouse effect, and indeed things like the amplification of the greenhouse effect by water vapor. So it's a very useful model indeed, but it's nevertheless an idealized model. Perhaps at a little slightly more kind of level of complexity, one could take the barotropic vorticity equation and write it in a somewhat idealized form, and do what Charney and Devore did some years ago by doing a kind of a maximal truncation of this equation, assuming very kind of coarse topography across the Earth, and basically boil this down to a three-component set of ordinary differential equations, and show that things like westerly flow and blocked flow exist as multiple equilibria on this set of equations. So we have a very nice idealized theory for why we get persistent blocking anticyclones. So people who've lived in the UK for the last 6 months or so will know that we've lived more or less under an extremely, I mean, people coming today will wonder what I'm saying, but it has been extremely dry for the last 6 months or so. A number of local authorities have water restrictions and so on, because we've been living under one of these sort of quasi-multiple equilibria. So a very nice idealized model for trying to understand the basic dynamics of this type of climate variability. The second class of model is what I'll call ab initio, in the sense we try to derive climate and all of the properties of climate from what we think of as the relevant basic laws of physics. And at the heart, one could think of the Navier-Stokes equations as being at the very basic level for fluid mechanics. So instead of idealized mathematically tractable models, we try to derive properties of climate from things we know are not mathematically tractable in any simple sense and need phenomenally big computers. And of course, one of the things one can point towards is the success of weather prediction. That's been, over the last several decades, quantifiably successful, I think, science, and it's come about because the models, the weather forecast models, are as much as can be done based on these first principle types of equations. Climate modeling, as we'll come to, is a rather, in this sort of ab initio sense, has become a rather complicated venture these days, in fact phenomenally complicated. In fact, one could probably say there is no more computationally complex problem in computational science than climate modeling and climate prediction from this ab initio kind of concept. So this is a very familiar, I'm sure to people who deal with climate models, a very familiar picture about how models have evolved over the years, from atmosphere-only models in the 70s to models which then couple the land surface in the 80s to the land surface and the oceans and the cryosphere in the early 90s, and now we're putting in aerosols, carbon cycles, and other types of chemistry into these models, so they're becoming more and more complex. 2 points about this diagram which I don't like. In fact, there are 3 things altogether about this diagram that I don't like. 2 I'll tell you now, and the third I'll leave for a little bit later. The fact that all these are sort of the same size, I think, sort of suggests that non-sulfate aerosols, important and complicated as I'm sure they are, have the same level of complexity as the atmosphere. But of course, the atmosphere covers a whole variety of important processes, from boundary layer turbulence, topography, and of course clouds, deep convection, all those sorts of things, radiation. So there's a whole plethora of things that's hidden in this one box here. The other thing one perhaps might think from this diagram is that now here we are in the 21st century, surely at least the atmosphere we've sorted out. I mean, the cutting edge is sort of down here in chemistry. Well, that's, as I'm sure most people who work in the field know, that's not the case at all. There are, and indeed, as I shall talk about in this talk, there are many issues in how we represent the atmosphere in climate models, never mind these other things. But nevertheless, this is showing the complexity of this sort of secondary approach. Well, why do we need these ab initio models? Why is there so much investment in them around the world at different meteorological institutes? As I say, we can sort of calculate what the temperature of the Earth is in some approximate sense from idealized models, but we immediately run into problems. For example, in this equation, A is thought of as a parameter, some albedo that you would specify, and of course albedo depends on cloud cover and ice cover and so on, and that's a function of the internal dynamics of the atmosphere, which might which would indeed contribute to the specification of the temperature. So in some sense, A, although it's hidden here as a parameter, contains a whole plethora of complicated dynamics. And the whole point of ab initio models is trying to not to specify things like albedo in general, or things like climate sensitivity. This is a point I find is not understood by a lot of the non-scientific community, who think that climate models we just specify as parameters things like climate sensitivity, how much the Earth is going to warm by a doubling of CO2. And it may be in some of these idealized models that climate sensitivity is a sort of parameter or effect, or it depends on some idealized assumptions. But in principle, at least in these ab initio models, we're not going to do that. It should derive from basic principles. So that leads us to the whole issue of the IPCC which feeds into climate mitigation talks, the Kyotos and Copenhagens and so on, which, well, we can talk about how successful or otherwise they are, but nevertheless, the basic scientific input to motivate those mitigation talks is coming from these class of models through the IPCC. They play a very important component in those discussions. I also want to just point out a couple of other applications in the climate area of ab initio models. I think governments around the world are increasingly thinking that, okay, if we cannot come to any great agreement about cutting emissions, we at least have to think about how society regionally should adapt to climate change. And then you need to know things like, will blocking anticyclones become more, for example, as far as the UK is concerned, will blocking anticyclones become more or less frequent under climate change? If they're becoming more prevalent, then we need to think about building more reservoirs. This was a period of time a couple of years ago where there was very prolonged drought and people started talking about building a national water grid, like we have an electricity grid, a water grid that would pump water down, say, from Scotland or somewhere where it was raining a lot down to more drought-prone areas of the UK. On the other hand, if blocking were to become less prevalent under climate change, then this would be a bit of a waste of time. So it's really quite important that we have a good quantitative grasp about how regional climate change will occur if CO2 continues to rise. And then the third application of these types of models, this is a kind of a bit of a science fiction picture, but something which is considered to be plausible, and is one example of these so-called geoengineering options. If we cannot agree to cut emissions of CO2, maybe we should find other ways to cool the planet. This is one where we spray salt water up into the clouds and increase the albedo. Again, the albedo comes in of the clouds, and that somehow cools the planet. But the question you should ask yourself, I think, is that whilst one can very simply put this type of effect into an energy balance model and indeed show it has the effect that one might think in terms of the gross radiative budget of the Earth, do we know what we're doing to El Nino, to monsoons, indeed to blocking anticyclones? And I think the answer is we haven't got the remotest idea at present. This is one example, spraying sulfuric acid into the stratosphere. Could be another one. But unless we understand what's happening to regional climate, I don't think anyone would even vaguely consider this as a plausible alternative to mitigation. So this is a third I'm just going through this as reasons why, although there is important work being done, I'm sure by many of you, in the sort of first class of model, the second class is nevertheless a very important one in our community. And this brings me to what I think has been a sort of a paradigm in, at least say in the 20th century, that broadly speaking, let's say mathematicians who are interested in climate, maybe one could say the academic community more generally, are the people that tend to focus on this first class of model with the objective of improved understanding of the climate system. And broadly speaking, I know this is a little bit of a broad brush statement here, but broadly speaking, this ab initio, which perhaps more pejoratively is sometimes called the brute force approach, that would be left more to the sort of software engineers that work in, say, meteorological institutes and climate centres around the world. So it's a bit of a kind of a two-class system almost that I think has developed over the 20th century. And I want to propose that this paradigm, if you think it has some truth in reality, is now becoming outdated. And I want to propose a new paradigm for the 21st century. And the reason I'm going to do that, propose this new paradigm, relates very much to the heart of this program. And I should say this talk is, I hope, more in the way of a motivational talk. I'm not going to go too much into mathematical details here, but I'll point to talks later in the week. All right. So why do we need to break down this this sort of I'm going to call it two class structure, or I'm trying to think of the phrase that C.P. Snow used, two cultures, yes, two culture community. So let's just think about the standard ansatz for a weather climate model. So we start with our PDE, which we think we know, and we project it onto some basis, grid points, spherical harmonics, whatever it is, finite elements, and we're left with things that we can't resolve explicitly. And I think probably going back to L.F. Richardson himself, I'm sure motivated by Reynolds' work in turbulence theory, we try to represent those unresolved processes by these what I call local bulk formula parameterizations. So this is some formula which depends on the variables at the truncation scale and a number of parameters which we set hopefully by appealing to observations or some such thing. So in the case of momentum for the atmosphere, we worried about the effect of representing turbulence in the boundary layer. Things like the effect of subgrid topography, which might be associated with excitation of gravity waves, which might well propagate out of the boundary layer up into the lower stratosphere or even mesosphere and deposit momentum quite remotely in terms of vertical location from the source region, maybe transport by convective clouds. I thought I would just show an animation talking about convective clouds, of what convective clouds look like from space. So this is an animation from satellites. These are convective plumes bubbling up. Sometimes these convective plumes sort of become organized and start to feel the rotation of the Earth. Those two nice tropical cyclones. But really I'm trying to get you to focus on these convective clouds. Each of these boxes is, I don't know, about 1,000 kilometers, say. So a typical climate model grid box would be some fraction of that. And you can see, broadly speaking, that the number of these convective systems per grid box is rather small. And this rather conflicts with the notion of bulk formula parameterization, where we kind of assume, so this is a schematic of one of these convective clouds in the tropics. That was the Western Pacific region, by the way. We kind of assume, for the purposes of deriving a bulk formula parameterization, of some large ensemble of cloud systems within the grid box in some sort of quasi-equilibrium with the large-scale flow. Much like we would try to parameterize viscosity or diffusion from considering the individual molecules within a sort of macroscopic zone and saying, okay, the mean free path between the molecular collisions is very small compared with the scale that we're interested in. And you can see from that animation that that's hardly a good approximation when we're looking at some kind of convectively active region. It might be true, for example, where we're looking at little puffy cumulus clouds, which I don't think we have today, where maybe there would be a lot, but little individual sort of shallow cumulus clouds don't contribute greatly to, say, latent heat release in the atmosphere, whereas these deep convective clouds contribute substantially. But they don't satisfy this kind of quasi-equilibrium consideration. I might say that very similar considerations could apply to other parameterized processes, things like subgrid scale, the effects of unresolved orography. One could assume there's a whole ensemble of subgrid gravity waves which are somehow propagating up into the stratosphere and breaking. But in reality, when one looks at the flow associated, if this was 100 kilometers of subgrid topography, one is probably seeing a dominant effect of one or two major subgrid orographic systems rather than a big ensemble of small orographic systems. This is a very famous diagram by Nystrom and Gage and co-workers looking at the energy spectrum of the atmosphere from scales of 10,000 kilometers down to sub-kilometer scale, and showing that there really is no sort of scale separation that one might have wished for if one was to try to parameterize some sort of bump in the energy spectrum at small scales. There's this gradual tail off, and in fact it becomes shallower as one gets below, say, a few hundred kilometers. So in the scale, in the region where we're trying to parameterize, which if we're talking about a typical grid size for a climate model being, I don't know, let's say 100 kilometers, we're in this rather shallow so-called 5/3 spectrum. So the theoretical basis for this bulk formula parameterization is rather weak. This is a slide which I'm not going to talk too much about, but my colleague Glenn Schutz, I think, will be talking in more detail later on about trying to use sort of new generations of models which are limited area by necessity, computational necessity, but can get down to scales of what are called, anyway, cloud resolving. To the extent to which they really are cloud resolving is a matter of some debate, but no, they're called cloud resolving, and with grid sizes of about 1 kilometer. And we can kind of test the bulk formula approach by assuming the cloud resolving model is truth, and doing then a coarse-grained budget over, say, well, in this case, 50 kilometers. So imagine a coarse-grained grid more typical of a global GCM climate model of 50 kilometers square, and look to see whether the within this 50 kilometers coarse-grained grid, whether the subgrid tendencies can indeed be describable by a bulk formula parameterization. And what these three sort of histograms show is a typical spread of subgrid tendencies associated with convectively active situations, where first of all you've got sort of weak convection, moderate convection, and strong convection. And in a nutshell, if the bulk formula parameterization was correct, we would expect these PDFs to be basically sort of be delta functions with a width of one of the boxes. And the extent to which this spread is not a delta function is a measure of how the bulk formula is failing. And what you see is as the convective activity gets stronger and stronger, so the departure from this kind of idealized delta function gets stronger and stronger. So we really are breaking down in a major way when we get to strongly convecting situations. As I say, Glenn will talk a bit more about this because it's an important, I think, technique in developing these ideas. So this was put a little bit more succinctly some years ago now by Scherzer and Lovejoy, fortunately in the days when slides were in black and white. So here we have our poor defenseless partial differential equation, which is essentially Navier-Stokes with all its scaling symmetries that it has. And here are these GCM global climate model kind of butchers, as it were, kind of chopping the hands off these poor guys. And I think you get the picture, right?
Doing violence to the equation.
Doing violence, yes, doing some violence. So, do we have an alternative? And this is the area where I've been myself kind of quite both interested and active in the last few years about trying to think of alternative approaches to this whole issue of subgrid representations. So I'm trying to say it's important because if we value the work that we do into guiding policy and helping society with these difficult climate change aspects, I think this is a key issue. And the idea is, can we represent these bulk? Is there an alternative to the bulk formula where we replace the bulk formula with some? Clearly, it has to be computationally cheap. Otherwise, we might just as well continue the original equations on ad infinitum. I'm going to stress here this word stochastic for a number of reasons in a minute. But somehow models which will be nonlinear and have some dynamics, but necessarily some stochastics as well. The key kind of concept here is each realization of one of these models would give a specific realization of potential subgrid motion. And by running this model in an ensemble mode, one then would generate the sort of statistics that one would need to describe the mean effect, say, across the grid box. So instead of trying to provide some ensemble average that doesn't really exist, for reasons I've spoken about, one tries to come up with a model which provides specific realizations of subgrid motions, and the ensemble statistics is then provided by running the full model multiple times with different realizations of the stochastics. Now, as I say, I'm not going to dwell in this talk on any sort of mathematics here, because I think this will come out in talks throughout this week. One idea that we've been using, a very simple idea actually, at ECMWF for many years now, is actually to take the standard parametrized tendencies and multiply it by some stochastic process. You could think of this, as I say, as multiplicative noise, in the sense that when the standard parametrized tendencies are small, in grid boxes where the parametrized tendency is very small, this stochastic term would itself be small. And when the parametrized tendencies are large, for example, over the Western Pacific region, the stochastic term would be large. An idea which I think Glenn will talk about later on today is this idea of stochastic backscatter. That the idea here is that if you think of think of the convection problem, in some sense what the parametrization is trying to do is take what was, before the time step began, a convectively unstable profile, and it will adjust the temperature and the moisture, for that matter, and maybe the momentum, but it will adjust things so it kind of gets back towards convective neutrality. Now you can ask, what's happened to the energy? I mean, in real convection, when you have convectively unstable profiles and convection is triggered, you obviously generate kinetic energy from that potential energy source. So in a parametrization, how is that energy accounted for? What happens to it when all the adjustment has taken place? Well, what happens is the energy is effectively dissipated within the grid box, and you can actually estimate from the parametrization how much dissipation occurs. So then you could ask yourself, in reality, is it the case that all that energy would be dissipated? And looking at examples of those convective clouds over the Western Pacific, where they actually kind of reach quite substantial scales, one can actually show that some of this energy starts to be converted from just simple overturning sort of divergent kinetic energy to rotational kinetic energy, and then can start to cascade upscale, feed upscale to sort of what would be resolved scales in the model. So the idea of backscatter is a kind of physical process that doesn't really exist in conventional parametrization, to allow energy to feed directly onto the resolved grid of the model, coming from a subgrid process. And how that energy is actually fed onto the grid, again, comes down to the stochastics. It won't be a deterministic function, it'll be a stochastic function. Anyway, I'm going to race through this. There are other ideas in cellular automata. Can we use simple ideas of cellular automata to describe, for example, convective, the motion and evolution of convective plumes, or indeed orography? I've long been kind of interested in this as an area for representing subgrid orography as well. Perhaps there are more generalized ideas here which relate to cellular automata and stochastic lattice models. And there are ideas in dual grid stochastic mode reduction. We'll hear about this. Statistical mechanics of finite-sized cloud ensembles. Can we use statistical mechanical thinking to guide representations of cloud systems when we don't have a very large ensemble but a finite-sized ensemble? Then I've got two things in brackets here which I think are closely related, but I put them in brackets because as they're currently formulated, they're probably not strictly stochastic. One is an idea, for example, that was used in the climateprediction.net project. It was a very imaginative project of getting people around the world to run a climate model, but with varying parameters. Each version that people would integrate on their PCs would have slightly different parameters, alpha, to others. So in the sense that each model is bit reproducible, this is not technically stochastic, but you could think of this as a way to treat these parameters alpha as stochastic, so it's quite close to being stochastic. And then there's the idea of sometimes called superparameterization, which has been pushed at the Colorado State and at NCAR as well, I believe, of trying to actually use simplified cloud-resolving models, typically two-dimensional rather than three-dimensional, within a grid box rather than the bulk formula. So again, this is very much in the mold of this thinking more imaginatively about the subgrid problem. But as far as I know, as yet, the superparameterization is still a deterministic model rather than a stochastic model. So I put it in brackets there, but probably there's not too much needed to generalize that. Okay, I want to just give you, in this talk, 5 reasons why I think this is worth doing. I mean, keeping aside as given the sort of societal importance of climate, but just from a science point of view, why might this approach be worth pursuing? Okay, the first is as a possible new approach to reducing model bias. So I want to talk a few minutes about model bias. This is a figure, actually it's 2 figures sort of superimposed on each other, which you might be a bit shocked to see, actually, if you're not so close to the climate community. But I think it's something that needs to be said. It's something Lenny Smith, who, I don't know if Lenny's at this talk, no, has certainly been quite active in advertising. So if you look at the idea is you're trying to replicate, can climate models replicate the temperature record of the 20th century, surface temperature record? So I think the black line here is the observed global temperature from the early 20th century through to the end of the 20th century. And these are a number of climate models where you can't see them, an ensemble of climate models which have gone into the AR4 simulations, which show, and the red is the ensemble average of all those different integrations, and you see that it replicates, you know, in sort of general sense quite well the 20th century trend. However, what is usually not made very clear in this figure is that the black line is an anomaly in the sense that it represents the departure of temperature from some long-term average. And similarly, all these green lines are anomalies. But the key point here is they're not anomalies with respect to the observed temperature, but they're anomalies with respect to the model's climate, what the model thinks is the climate of the long-term climate of the 20th century. So implicitly, you're subtracting out of this figure here the biases that may or may not exist for each of the climate models that go into this ensemble. And if one was to not do this implicit bias correction, but just plot temperatures as temperatures in Celsius, I guess this is, then you actually see that there's a fantastic range of temperatures that the AR4 models have, and implying that the biases are quite strong. Now, it hardly needs to be said that if one is dealing with a highly nonlinear system, which we are dealing with, it's hardly satisfactory that we have these quite substantial biases in something as basic as global mean temperature in the models. And clearly, to have confidence in our predictions, we really do need to, I mean, it's just clearly not good enough to subtract the biases in a linear sense for a system that's highly nonlinear. So this is a long-standing, issue. Climate models aren't bias-free. And we see that also when we come to look at more regional quantities. So coming back to the persistent blocking anticyclone. So you might have thought if Charny-Devore can model a block with just 3 components, then a climate model with many millions of components should do super well at getting it. But unfortunately, life isn't that simple. Probably the key thing that's ignored in Charny-Devore is the transience that actually gives the the block its sort of chaotic nature, the fact that blocks clearly aren't precisely multiple equilibria. They're persistent flows, but they vary, they come and go irregularly and chaotically. And it's believed that the transient activity of baroclinic waves, so even though blocking itself is a predominantly barotropic phenomenon, the interaction of the baroclinic waves, the weather systems, play a key role in maintaining and indeed destroying these blocking anticyclones. And this is a snapshot of potential vorticity in the upper troposphere, showing what looks like a kind of wave breaking process going on, whereby a baroclinic, a weather system is kind of feeding potential vorticity into the block and maintaining it. And you see there's quite some sort of filamentary structure to these PV potential vorticity patterns, and again suggesting that to get that interaction correctly, one needs quite high resolution in one's climate model. And so this was from a project called Demeter, which I was involved with a few years ago, looking basically at IPCC AR4 class models and looking at how well they simulate these blocking anticyclones. So this is longitude running along here, frequency of blocking. The red is the observations. There are two peaks of blocking in northern mid-latitudes in winter. The red shows the frequency of the climate model. This is a French model, ECMWF, Met Office, and you can see they're all under simulating. They all under predict frequency of blocking. So again, that's another type of bias, and I think a rather important one in our climate models. I might say, just by the way, this is not purely of academic interest about blocking. This is just show you for 2 minutes. A really quite important study came out from the Met Office last year called the UK Climate Projections 09 report, and this was supposed to, and indeed does, provide guidance to the UK government and institutions about how one should be adapting to climate change. And they put out projections of temperature and precipitation, but didn't put out any projections of windiness. And this was from the report, and this blocking was clearly considered to be a crucial aspect that was so poorly represented in the models that they felt unable to put out projections of wind. So the mechanisms for atmospheric blocking are only partially understood. It's clear there are complex motions involving mesoscale atmospheric turbulence and interactions that climate resolution models may not be able to fully represent. In developing the UK CP projections, it was decided not to include probabilistic projections of future wind due to the high level of associated uncertainty. Now, I say it's not of academic interest because the UK is certainly putting a lot of focus and a lot of its renewable energy policy into offshore wind. And one could ask the question, based on the current generation of climate models, can we be confident that there will actually be enough wind to drive these renewables to provide the amount of electricity they are projected to, the fraction of energy that they will, of the total energy requirement for the country that they are projected to provide, 30% or something, will they really be able to do that given future climate change projections of windiness? Well, the answer is we just haven't got a clue. We don't know. So this is a rather serious problem. It's not just an academic problem. So my first point really is that that stochastic parameterization has the potential, at least, to affect, and hopefully improve some of these biases. And just a very simple picture you might want to keep in your mind is of a potential well, and of imagining a system which is, but nevertheless a kind of a slightly skewed potential well, a system that oscillates between near the minimum with weak noise and here with strong noise. The mean state of the system will depend on the amplitude of the noise. So as the noise gets stronger, so the mean state shifts systematically in the direction where this potential is flat. And some studies that Judith Berner here did when she was at ECMWF show this potential as it were, being realized. So this is the red. The colors here show you the bias in this is the version of the ECMWF model that's used to make seasonal climate projections. So this is, in some sense, a current version of the model for our seasonal forecasting system. And it shows the bias of the model of one of the variables, the 500 hectopascal, the height of the 500 hectopascal pressure surface, showing that it's too low in high latitudes and too high in sort of subtropical latitudes. Now we know this is the spectral resolution of the model, T95, so the grid of there's a few hundred kilometers. We know if we increase the resolution, we can ameliorate that bias. So this is the impact of increasing resolution by a factor of 5. But that's computationally very expensive if one's doing seasonal climate integrations. But nevertheless, these yellowish colors means that the height has increased relative to the low resolution model, as it were, filling in some of this bias. But this is a much more computationally cheaper type of integration, which keeps at this T95 resolution, but it adds some of these stochastic parameterizations, and I think in this case notably the backscatter parameterization. And it has a somewhat similar, well, it's not identical, and there are obviously statistical uncertainties here, but to sort of crude estimate, one could say it's doing a somewhat similar job to the increase in resolution. So this is illustrating the potential, at least, for some of for this type of approach to have an impact on some of these very long-standing biases that exist in climate models. So that's reason number 1. So I've still got 4 more reasons to go through, but I'll try and do that in the time. Yeah, so I mentioned that there were 3 things I didn't like about this diagram. If you remember, one was the idea that the atmosphere box is as big as some of these other boxes. Well, it should be a really big box. And the other was the kind of suggestion that the cutting edge of science is down here, and this is all, this is all done and dusted, which is not true. But there's a third reason which I don't totally like this figure, and that it misses out what I think is a very important, let's say, variable that needs to be forecast if one, so an Earth system model at least purports to be some sort of comprehensive representation of climate. And I would claim there is one more variable that is needed here, at least one anyway, if one really is to purport to be a comprehensive prediction tool. And that missing box, if you like, is uncertainty. How uncertain are our projections? Now, the standard approach to uncertainty, for example, in the IPCC fourth assessment, is to make use of the pool, if you like, of climate models that have been developed around the world. So individual institutes tend to have their own climate model. They all do the IPCC standard integrations, and they all put together in this big common archive. And from that, one can deduce or give estimates of uncertainty based on the spread of the predictions or projections. This particular slide is showing an ensemble approach based on just European models, which, again, I was involved in through an EU project called Ensembles. Very cleverly, I don't know who did this, I always think it was a rather cute thing to take the stars of the EU and draw them into a Gaussian. I thought that was a rather neat idea. Wish I'd come up with that, but it wasn't me. Anyway, in this particular project, there are a number of, so the Met Office, this is in ECMWF, so Métier France, Italian, German model, they all went into making a multi-model ensemble. And we tested the skill of this ensemble, not only looking at the long-term climate change type timescales, but also seasonal climate timescales where we can verify the forecasts. And in fact, what we did was to compare the multi-model ensemble approach versus this perturbed parameter approach, which I spoke about, the one that was pursued at climateprediction.net, and also is the way the Met Office creates it's the way the Met Office represents model uncertainty in its decadal prediction system by running ensembles with variations of these parameters alpha in the bulk formula parameterization. And then the third one was this stochastic approach based on the first two of that long table I had, the multiplicative noise and the backscatter. I just want to show you a couple of results, and I realize I'm not giving you too much detail here, but I just want to give you a kind of flavor of where I think we are at the moment. What we're going to do is verify these forecasts over these different regions, which are sometimes called the Georgi regions of the world, and I'm going to verify them in terms of precipitation and temperature based on how well they do seasonal forecasts. For the record, for those of you who know about these things, the actual skill score measure is called the Breyer skill score. It's a way of assessing the skill of a probabilistic forecast, so a system that produces a PDF for its output. And it's taken over a whole set of seasonal forecasts from 1991 to 2005, so they're hindcasts, as it were, rather than real forecasts. And I've boiled it down here. This is work, by the way, done by my colleague Antje Weisheimer. I've boiled it down here into a set of colours, which, rather than kind of giving you numbers, which would be rather dry and difficult to see, which just says which, and we're looking, I don't want to go into too much detail here, but we're looking at forecasts made from May of the summer season or from November of the winter season, and we're looking at probabilities of, this dry means the lower tercile of rainfall, climatological tercile, or the upper climatological tercile. And where it's red, the multi-model ensemble is best of all of those three systems. Well, actually, no, four. We've got four systems here. Multi-model, the perturbed parameters, stochastic physics, or no representation at all of model uncertainty. So you just run an ensemble in this grey box. It means you've run an ensemble with just perturbed initial conditions only and no representation of the model uncertainty. So for this particular thing, okay, having no representation of model uncertainty definitely does worst. 10% of the cases it's best, but it's a kind of that's, I guess, within the statistical fluctuations. The best of them is the stochastic physics, with 45% of cases being where it's best, and the multi-model would be next, 24%. So in this case, for this particular variable, this stochastic representation is really doing best as the best representation of model uncertainty. Now, for temperature at the surface temperature, we get a rather different story. Here, the multi-model system is best with 38%, and stochastic physics is second with 30%. So we're seeing a slightly different picture depending on which variable we look at, precipitation or temperature, and I'll explain why I think there are differences later on. But the point I want to make here is that this stochastic method is starting to become kind of competitive with the multi-model approach. 10 minutes. So that leads me to the third. I'm going to get through these five and then I'll probably finish. The third reason why I think this is important. And it's related to that last slide. If we think this stochastic physics approach could be competitive, then what are the implications of that for the way we do climate modelling? Just want to again come back to this picture, because if you think about this, if each institute has to develop an Earth system model, and maybe it has, 20 people in its institute that can do model development, given that the atmosphere has turbulence, orography, radiation, clouds, convection, other things, that's the atmosphere. Then there's the land surface, soil moisture, all the vegetation, blah, blah, blah. The ocean, dynamics, cryosphere. You've got hundreds of things which is being spread across a small number of people. Is it really sensible that individual institutes have the capability to do this? So I'm reminded of the way things were in the 60s with respect to civil aircraft manufacture in Europe, where every major country had its own civil aircraft manufacturer. And then it was realized this is terribly inefficient. We're all sort of doing the same things. And aircraft have become incredibly complex with computer technology and all the rest of it. And the way we've approached this in Europe is through a consortium approach. The question is this a good approach for development of climate models? Now, the standard argument against what I'm calling this Airbus paradigm applied to climate modeling is that we need model diversity. You know, it's wrong to put all our eggs in one basket. We need model diversity in order to be able to estimate our confidence in our predictions, or to be able to estimate the uncertainty in our predictions. However, if we can show objectively through these alternative methods for developing climate models that we can actually do better than, or at least as well as, if not better, than the pool approach, then that really undermines that argument, and it makes the argument, I think, stronger that we should be thinking much more about how to make more efficient use. I mean, let's say, I realize people now are here from all parts of the world, but let's, for the sake of argument, think I'm talking about Europe, although it doesn't necessarily have to be Europe. I think an approach which can, within a single modeling framework, do as well or better in representing uncertainty and confidence than this rather ad hoc multi-model approach, if that is the case, then I think it really makes us, and it should make the directors of institutes think very carefully about the most efficient deployment of human and computer resources for developing climate models. So I see this whole program here as having an enormous potential sort of sociological has enormous sociological implications for how as a continental or indeed global community we go about developing these important models. And then, as I'm coming to the end, I just want to mention something which I think is a curiosity at this stage, but is one perhaps worth thinking about in the future. I came across this a few years ago of an approach to computing. It was motivated by the fact that we're getting in computing hardware and now really seem to be close to the limit where energy dissipation, per cubic nanometer or something, is the limiting factor in getting individual processors to perform at maximum speed. And so the trend, as you know, in computing these days has been to have larger numbers of processors in a computer. This approach has been to try to get over that sort of restriction by asking, is it absolutely necessary that we demand bit reproducible results? If we don't demand absolutely bit reproducible results, we maybe don't need to be feeding all these transistors that we have with such high voltages and therefore high energy dissipations. And an approach to developing computer chips which have much smaller energy requirements, keeping the speed, but somehow breaking this bit reproducibility. I noticed this in a technology review magazine a few years ago. And sorry about this, but this is something which a colleague gave me just last week of this is just on the web, so August the 17th, so it was just last week, of a company called Lyric Semiconductor. Now, I might say I don't have shares in Lyric Semiconductor, so I don't even really know who they are, but I couldn't help, it just sort of couldn't help noticing this. So Lyric's, what would I say? Lyric's probability processing technology calculates in a completely new way, enabling orders of magnitude improvement in processor efficiency. Blah, 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 blah. Here we are, this will do. As a result, many applications that today require 1,000 conventional processors will soon run on one Lyric processor, providing 1,000 times efficiency in cost, power, and size. So the question is, and this is, again, a bit of a break from the tradition of meteorological institutes where bit reproducibility has been an absolute sine qua non, as it were. Is this a way to actually make much better efficient use of computing hardware that can utilize this type of essentially stochastic type of formulation in much more efficient ways than conventional models can? All right, and my fifth reason is because the boss said so. So this was from 1975, so if you believe nothing of what I've said so far, then at least believe this. I believe that the ultimate climate models, says him, will be stochastic, i.e. random numbers will appear somewhere in the time derivatives. Okay. So, just want to say where we are at the moment. I'm speaking now slightly parochially in the sense of my experience at ECMWF, and there are probably people here who will contradict me a little bit in this. In the atmosphere, we've got these schemes. This is this multiplicative noise, this is this backscatter, partially addressing some of the issues in the atmosphere, by no means all of them. I would say one thing that we're absolutely missing at the moment in the atmosphere is the representation of stochasticity in clouds themselves, and the effect of clouds on radiative properties at the surface. And my own feeling is that result I showed you earlier, where we did quite well in precipitation scores, but less well against the multi-model in terms of surface temperature, I think is partly due to a lack of stochastic representation of the radiative transfer properties associated with subgrid cloud. So subgrid cloud amount would be considered a deterministic quantity parameter in conventional parameterization. So only at ECMWF we've done nothing at all on these other areas, and I don't see why they should be any less amenable than the atmosphere. Okay, I'm skipping over this because we don't have time. So, my virtually last slide, this is the challenge which I promised you at the beginning, which is I think that mathematicians, many of you in the audience, and props to the academic community more generally, really needs to help now to generate or develop a new generation of ab initio system models. Let's throw this paradigm where it's just the software engineers in the Met offices of the world do the model development, and let's acknowledge that the mathematical science community has enormous skills that I think can be brought to bear in this whole area of Earth system model development and the new generation of and the new generation of such models. And in particular, replacing these bulk formula parameterizations with innovative stochastic dynamic mathematics to aid our ability to predict climate for the good of society worldwide. The tools we have to work with are observations, cloud resolving models, and I stress this, and I think there'll be further talks later this week which will develop this theme. And of course, we have physics, mathematics, and the power of pure reason. So I just finished putting the grand challenge back up again, and thank you for your attention.
Tim, do you think it's reasonable that you can actually backfit these stochastic models into the existing climate model framework? Because to me, there seems to be a bit of a contradiction. The climate models have been quite carefully, or weather models have been carefully tuned. And so you put back then a stochastic model which is trying to reproduce realizations rather than some sort of average flow. There's a mismatch there, isn't there?
I think you're right. I have to say, in the context of what we've done at ECMWF in the last decade or so, it actually pretty much has been in this sort of backfitting mode, because the multiplicative noise parameterization really is just taking taking the standard parameterization bulk formula standard parameterization package and sort of pre-multiplying by a stochastic process. So that's a kind of fairly, conceptually a fairly sort of trivial thing to do, and enables one to to take pre-existing models and do that. But actually, it's been surprisingly successful in terms of what was our primary aim, which was to improve the reliability of our ensemble weather prediction system. So it improved these Breyer skill scores. But I have to say, I think you're absolutely right. I mean, more generally, it needs a bit of a culture change from the people that really do the work on parameterization from the basics. And I think this is where we, as a community, really start to, I would say, sort of need a better dialogue, that these things should be built in really from the basic, at the very basic development stage, and not just as something, as you say, one would backfit. So I think we're at the stage now where we are backfitting and showing some benefits, but it's by no means optimal.
I'm a little puzzled as to where the spread in equilibrium responses is going to come from a model. I would have thought that in the long run, over a long enough integration, whatever your initial seed is, the climatology of the model will be whatever will be fixed, and the climatological response to external forces will also be the same.
Could you repeat the question because it's not clear at the back?
I'm wondering where the diversity in equilibrium responses is going to come from a model with with stochastic input.
Well, I think what I'm saying, perhaps in answer to the second question, is that looking forward, one needs to, when one is developing these subgrid parameterizations of physical processes, the actual uncertainty, for example, uncertainty in the closures that are used, or uncertainty in the parameters that are used, or uncertainty in the formula, the mathematical structure of the parameterizations, needs to be built in as a basic kind of construct in the model, so that one can, for example, if there are a set of models of the multi-model ensemble, which in some sense one could say are equally likely, they should emerge as realizations of these stochastic representations within a single framework. So that would be the intention, at least. I'm not sure. Is that answering your question?
Well, I don't think so. If you go to the example you showed where you tried the stochastic physics in the ECM model, I mean, if you run each of those model instances on for 30 years, do they each have the same bias in the climatological statistics relative to observations, or do they have a range of different biases in different regions over a long time period?
I mean, we're trying to design a model which has no bias. I mean, the bias is something that we know should be, within sort of statistical fluctuations. But I mean, we're trying to reduce the bias. We're not trying to get an ensemble of models, each of which has different biases. That would be the wrong thing to aim towards. We're trying to aim towards.
Okay, but given that the model will always have bias, the question is: do you want an ensemble of models that have different biases in different regions, or an ensemble of models that, as I understand it, the ECM model will always have the same biases?
Well, I think the idea is we're trying to minimise the bias as much as possible, but represent the range of uncertainty in the physical processes, which is inevitable given the need to do some sort of closure to the subsystems. So I don't think it's quite. I wouldn't perhaps phrase it that way. I think would be my answer.
Actually, can I press you further on that point? Because I feel that, I think that this question is consistent with the previous question, that when you've talked about quantifying uncertainty, you've kind of lumped together, on the one hand, multi-model ensembles, on the other hand, stochastic parameterization, right? And indeed, you've even compared them in a table with colours. But I mean, surely they're different animals, aren't they, which can't be compared? I mean, if I'm thinking about looking at a multi-model ensemble to assess model uncertainty, I'm thinking about how the climate of those individual models varies across the set of models, with the climate being defined by a PDF and all that. Whereas on the other hand, a stochastic parameterization is a tool for getting the climate. I don't see the equivalence of uncertainty in the two cases.
Well, in the case of the the problem in climate change is we don't know the truth, as it were. So we can use a multi-model ensemble to give us a range of possible future future projections for a given CO2 scenario, and say, okay, that's a measure of the uncertainty.
But are you meaning that uncertainty in the sense of, like uncertainty in the climate system? If you were to run different realizations of the real climate forward, slightly perturbed, we get different outcomes over the next 40 years, or are you thinking of different realizations? Okay. I mean, we take that's always taken into account, because inevitably, with one model, you would run an ensemble from different initial conditions, so that the what would be called the uncertainty due to internal variability, if you like, is taken account in an initial condition ensemble. So that aspect of uncertainty if one thinks one has a good model, that is relatively easy to take account of. You just run multiple realizations from slightly different initial conditions. But the question is, the fundamental important question is,
given that there is this second source of uncertainty, which is actually our computational representation of these equations, in addition to the, if you like, internal variability uncertainty, does a multi-model ensemble give us a reliable estimate of that uncertainty? For example, for making decisions about building new reservoirs, or think of something practical. Does that multi-model ensemble provide us with a realistic estimate of model uncertainty? Now, we can't test that in climate change because we don't know what's going to happen, at the end of the century. But we can use the same methodology for shorter timescale predictions where we do have the verification. So seasonal, multi-seasonal forecasts are something which test aspects of the coupled ocean atmosphere dynamics. They don't test all aspects, they don't test the cryosphere particularly, but they test a lot of atmospheric, cloud and ocean dynamics quite well. So we can say, okay, let's do this in seasonal forecast mode. We produce an ensemble which both has the internal variability, so we perturb the initial conditions, but has either this multi-model representation of uncertainty, that's system A, system B, if you like, is the stochastic physics. And there are objective tools which are these Breyer score type tools, for estimating whether these separate representations of uncertainty are good or bad. So, for example, if your verification lies outside the range of the ensemble, so you say, it's going to be a barbecue summer, plus or minus, 2 degrees. That's what all the members of the ensemble say. And the verification is it's a lousy summer, raining every day, and it's 10 degrees below climate or something. That's clearly a bad. Your estimate of uncertainty has been poor. And what I'm saying is that these stochastic methods, at least for some variables like the precipitation, but not all, are performing actually better than the multi-models, or at least as well. And so the implication is that they have the potential at least to do better, both objectively better and also better because they'll hopefully be based on more sound physics, more sound science than just let's take the pool of models that happens to be around in the world today as a very ad hoc, representation of uncertainty. Does that, I don't know, am I answering or not?
To some extent, I think. I think the point is, as you say, the multi-ensemble method is a very ad hoc way of doing it.
That's right.
Actually,
it is very ad hoc. So can we do better than that? And there are all sorts of implications if we can, in my view.
A couple more before we break for coffee. There was one there as a step.
Seems like there are two categories of parameterization that one could talk about. One is sort of boundary forcing, so interactions with the land surface and so on. And one could put stochastic representations of the parameters in there. And the other one is associated with a finite resolution of a 3D flow which has more complexity at small scales. And it seems like your rectification things are mainly playing to that aspect. Would you agree with that? And the follow-up is, if that's true, can we not use some of the resolved variability to inform the unresolved variability?
Well, I'm not sure. I need to talk to you about the second part of that question because I haven't fully understood that. I think you're right in saying that certainly what I've been focusing on here is, well, I've obviously put a lot of attention on the convection problem. So I'm just sort of thinking on my head now, because the other area that certainly interests me, where I think these methods have some potential, is actually the problem of topography, forced topography, and that sort of links a little bit to the land surface issues. So I think this is something to explore. I don't think there's a simple answer at this stage.
There was one more question over here, I think. Or has that been answered?
We're just going to say, haven't what you really proposed to be something in addition to parameter variation? Surely we're not going to stop varying our parameters, because your method is not going to tell us what the uncertainty is in the 21st century climate projection. That's going to tell us something completely different.
That's right. I think in a sense there is a kind of trivial way in which these parameter variations can be built in as stochastic variables. at the moment you just do multiple runs where the parameters are held fixed over the 100 years of each individual member of the ensemble. I mean, it would be a relatively trivial thing to make those parameters stochastic and maybe dependent on flow regime or something like that, which might make better physical sense. So so I certainly agree that I don't see this as an alternative, but we need to think, well, my feeling is that the parameter variation program needs to be built into the stochastic program more than it has at present, so it can be properly kind of unified, if you like, with these other approaches.
Let's take a break now so we've got time to catch a coffee. Should we thank Tim once again for a very interesting